What if I told you there's a single mathematical trick borrowed from image compression that lets the world's most powerful AI models run on a fraction of the memory they normally need, without losing any intelligence? That trick is called Multi-Head Latent Attention, or MLA. And by the end of this video, you'll understand it deeply, from the intuition a beginner can grasp all the way to the equations a researcher would write. Welcome! Today we are going to master Multi-Head Latent Attention. Let me first tell you why you should care. DeepSeek, one of the most talked about AI labs on the planet, uses MLA as the central innovation in their V2 and V3 models. Kimi K2, GLM5, Mistral 3 Large, and Sarvam 105B have all adopted it. When you see MLA in an architecture card, it means the engineers cared deeply about making inference efficient without sacrificing model quality. So understanding MLA tells you something important about how frontier AI works. Before we get to MLA, let's do a quick refresher on how transformers work. Don't worry, we'll keep it beginner friendly. A transformer takes a sequence of tokens, think of tokens as word pieces, like multi-head, latent, and converts each token into a vector of numbers called an embedding. These embeddings flow into attention layers, where every token can look at every other token and decide, how much should I pay attention to you? Standard attention uses something called multi-head attention. Instead of doing this looking around once, the model does it in parallel many times, each time with a slightly different lens. Each lens is called an attention head. For each head, we compute three things: a query, a key, and a value. The query asks a question. The keys are like labels on every token. The values hold the actual information. Attention scores are computed by matching queries to keys, and then used to mix up the values. Now here is the critical performance insight. During text generation, the model produces one token at a time. For each new token, it needs the keys and values of every previously generated token. Recomputing all those keys and values from scratch every step would be incredibly wasteful. So instead, we cache them. This is the KV cache, a memory region that stores keys and values for all past tokens so we can reuse them. But here is the catch. As you generate more and more tokens, the KV cache keeps growing. For a standard model with many attention heads, the cache size equals number of layers times number of heads times sequence length times the head dimension times 2 for K and V times the bytes per number. At 128,000 tokens with a large model, you can easily hit 40 to 80 gigabytes just for the cache. That eats up your entire GPU memory budget, and performance collapses as the system starts swapping to slower memory. Researchers noticed this problem and came up with partial solutions. Multi-query attention, or MQA, uses just one shared key value head for all query heads. This cuts the cache dramatically, but hurts quality noticeably. Then grouped query attention, or GQA, used in Llama, Mistral, and many others, found a middle ground: group the query heads into small clusters, and share one key value pair per cluster. GQA saves significant memory and is the current industry standard. But it explicitly trades quality for memory. The bigger the groups, the more you lose. DeepSeek wanted a better deal. Here is the key insight behind MLA. Think of it like image compression. When you save a photo as a JPEG, you don't store every pixel in full detail. Instead, you compress the image into a much smaller representation, the compressed bytes, and when you want to view the photo, you decompress it back to full quality. MLA does something remarkably similar with key-value pairs. Instead of storing full keys and values for every token, MLA compresses them into a tiny latent vector, just like a JPEG thumbnail, and stores that instead. When attention is needed, it reconstructs the full keys and values from those tiny latent vectors. Same information, far less storage. The mathematics behind this compression is called low-rank approximation. Let me give you the intuition. Imagine a giant spreadsheet with 1,000 rows and 1,000 columns. That's 1 million numbers to store. Now imagine that the rows are not all unique, they share patterns. Maybe most rows are combinations of just 10 basic row types. If that's true, you could represent the entire spreadsheet with just two smaller tables, one table of 10 basic row patterns, and one table saying how to mix those patterns for each row. That's 10 times 1000 plus 10 times 1000, just 20,000 numbers, 50 times smaller. This is low-rank approximation. The rank is the number of basic patterns, 10 in our example. If the rank is much smaller than the matrix dimensions, you get massive compression. Formally, a matrix M with n rows and m columns can be approximated as the product U times V, where U has n rows and r columns, and V has r rows and m columns. The number r is called the rank, or latent dimension. When r is much smaller than n and m, the storage drops from n times m down to r times open parenthesis n plus m close parenthesis, a huge saving. You might recognize this from LoRa low-rank adaptation, which uses exactly the same idea to fine-tune large language models with very few extra parameters. So how does MLA apply this to attention? Let me walk you through the architecture step by step. In standard multi-head attention, the input vector X is projected directly into queries Q, keys K, and values V using three large matrices. MLA replaces these direct projections with a two-stage process. Step 1. Compression. The input X is multiplied by a small compression matrix WKV down, producing a latent vector CKV. This latent vector has dimension R, which is much smaller than the full model dimension D. This latent vector CKV is what gets stored in the KV cache, not the full keys and values. One small vector per token instead of two large ones. Step 2. Decompression. When we need to compute attention, we take the stored latent vector CKV and multiply it by two decompression matrices, WK up and WV up, to recover approximate keys and values for each head. Each attention head has its own decompression matrices, so different heads can extract different information from the same compressed latent. The query side gets similar treatment. The input X is compressed into a query latent CQ, which is then decompressed into the actual query Q for each head. This reduces computation during the forward pass as well. Let's write the equations precisely. The KV latent is CKV equals X times WKV down. Keys are reconstructed as KH equals CKV times WK up H. Values are reconstructed as VH equals CKV times WV up H. Queries are QH equals X times WQ down times WQ up H. The attention output for head H is softmax of QH times KH transpose divided by square root of D head multiplied by VH. All heads are concatenated and projected by an output matrix WO. Now here is an elegant optimization called the absorption trick. Notice that keys are CKV times WK up H, and queries are CQ times WQ up H. When we compute the attention score Q times K transpose, we get CQ times WQ up H times WK up H transpose times CKV transpose. The middle part, WQ up H times WK up H transpose, does not depend on the input at all. We can pre-compute this product once for each head and store it as WQKH. This saves a matrix multiplication at inference time on every single forward pass. This is called weight absorption, folding weight matrices into each other. Let's quantify the memory savings concretely. In standard multi-head attention with H heads, head dimension DH, and sequence length L, KV cache size equals L times H times 2 times DH. In MLA, we store only the latent CKV of dimension R, KV cache size equals L times or DeepSeek V2 uses are equal to 512 while D equals 5120 and H equals 128. The full-size KV would be 128 times 2 times 64 equals 16,384 per token. MLA stores only 512, a compression ratio of over 32 times. At 128,000 tokens, this is the difference between 26 GB and under 1 GB. But does this compression hurt quality? DeepSeek ran careful ablation studies comparing MHA, GQA, and MLA across identical training runs. MLA matched or slightly exceeded MHA quality on nearly every benchmark. GQA with equivalent memory savings showed noticeable degradation. The reason MLA can do this is that the compression matrix is shared across all heads, so it learns a universal compressed representation of the sequence context, which each head then specializes from. This is strictly more expressive than GQA, where heads are simply grouped together with no learned compression. Let me walk you through exactly what happens token by token during inference. When token number 1 is processed, we compute its KV latent CKV1 and store it in the cache. When token 2 comes in, we compute CKV2 and append it to the cache. Now when computing attention for token 2, we decompress both CKV1 and CKV2 on the fly into keys and values, run attention, and produce the output. The cache grows by exactly our numbers per new token, regardless of how many attention heads the model has. This makes MLA cache growth dramatically slower than standard attention. A quick technical note on positional encodings. MLA uses rotary positional embeddings, or ROP, but applies them in a special way. Because the keys are reconstructed from the latent, we can't apply ROP inside the compressed representation, it would break the weight absorption trick. So DeepSeek's implementation decouples the position information, a small additional key component carries the ROP encoding separately, and is concatenated to the main key before attention. This keeps the absorption trick intact while preserving positional information. Here is exciting news: you don't have to train a model from scratch to get MLA's benefits. The Trans-MLA framework, published alongside DeepSeek v2, shows that any model trained with standard GQA can be converted to MLA by factorizing the projection matrices after training. The conversion finds the best low-rank factorization of the existing weight matrices using singular value decomposition. After a short fine-tuning step, the converted model matches the original quality while gaining MLA's memory efficiency. This means Llama, Mistral, and other GQA-based models can be upgraded. Let's survey the landscape of models that have adopted MLA. DeepSeek v2 was the first to introduce MLA at scale in 2024, proving that a mixture of experts model could be both efficient and powerful. DeepSeek v3 refined the implementation and achieved state-of-the-art results on coding and reasoning benchmarks while fitting in a dramatically smaller memory footprint. Kimi K2 from Moonshot AI uses MLA paired with linear attention for extreme efficiency. GLM5 from Tsinghua uses MLA in their dense model architecture. Mistral 3 Large adopted MLA for their flagship model. Sarvam 105B is a large multilingual model using MLA for efficient serving. MLA is not a free lunch, and I want to be honest about the trade-offs. First, implementation complexity. Standard attention is a clean, simple operation. MLA adds compression, decompression, and the ROP decoupling, roughly 3 times more code to get right. Second, the absorption trick requires careful bookkeeping. The pre-computed matrices must be correctly shaped and indexed. Third, latency. Decompressing the latent at every attention step adds a small compute cost. For very short sequences, this overhead may not be worth the memory saving. MLA shines when sequence length is long and memory is the bottleneck. When should you choose MLA? Use MLA when you are serving very long sequences, code generation, document understanding, long-form reasoning. Use MLA when GPU memory is your binding constraint at inference time. Use MLA when you need MHA level quality but GQA level memory. Stick with GQA when simplicity matters more than peak efficiency, or when your sequences are short enough that the covey cache is not the bottleneck. Let's bring it all together with a summary. MLA stands for Multi-Head Latent Attention. It solves the covey cache memory explosion by compressing keys and values into a tiny latent vector using low-rank matrix factorization. The latent vector, not the full keys and values, is what gets stored in the cache. At inference time, the keys and values are reconstructed from the latent on demand. The weight absorption trick allows pre-computing part of the attention matrix, speeding up inference further. Compared to GQA, MLA achieves higher compression with no quality loss. It is used in DeepSeek, Kimi, GLM5, Mistral, and Sarvam, and can be retrofitted onto existing GQA models via Trans-MLA. If this video helped you understand MLA, please hit like and subscribe, it helps more people find this content. Drop a comment below, which part was hardest to understand? I'll make a follow-up video on whichever topic gets the most requests. Thanks for watching. See you in the next one.